Deep within the cosmic tapestry of our universe, among the remnants of once massive stars, lies one of the most enigmatic and extreme objects ever discovered, the neutron star. When a star several times more massive than our Sun reaches the end of its life, it undergoes a spectacular supernova explosion, casting its outer layers into space. But what remains at the core is even more intriguing. A dense sphere about the size of a city, yet with more mass than the Sun itself. This is the neutron star, a stellar remnant so extreme that the laws of physics are pushed to their very limit. But what exactly is inside a neutron star? To begin to understand, imagine compressing the mass of the Sun into a sphere only about 20 kilometers across. The result is an object with gravity so intense, a teaspoon of neutron star material would weigh about 1 billion tons on Earth. This phenomenal density arises because, inside a neutron star, atoms are crushed together under unimaginable pressure. On the very surface of a neutron star, things are already bizarre. The crust is a few hundred meters thick and composed of atomic nuclei packed tightly together, surrounded by a sea of electrons. But as we move deeper, the pressure increases so dramatically that electrons are forced into the atomic nuclei, combining with protons to form neutrons. This process, called electron capture, transforms the familiar matter of the universe into something utterly alien. Beneath the crust lies the neutron star's outer core, a region dominated by a superfluid of neutrons. Superfluidity is a quantum mechanical phenomenon in which matter flows with zero viscosity, meaning it can move without any loss of energy. In the outer core, neutrons, along with a sprinkling of protons and electrons, behave like a single coherent quantum state. This superfluid can also conduct heat and electricity with astonishing efficiency. Diving further, we reach the inner core, the heart of the neutron star. And here, the mysteries only deepen. Scientists believe the densities and pressures inside the inner core are so extreme that the very nature of matter may change. Protons and neutrons themselves could break down into their constituent quarks, forming what's called quark matter, or even a quark-gluon plasma. This is a state of matter that hasn't existed naturally since the earliest moments after the Big Bang. Some theories even propose the existence of exotic particles such as hyperons, particles containing strange quarks, or condensates of pions or kaons. These possibilities are the subject of intense theoretical research, as we have no direct way of probing these inner realms. The gravitational field of a neutron star is so strong that it warps space and time itself. Light escaping from its surface is redshifted, stretched to longer wavelengths by gravity. The magnetic fields of neutron stars can be trillions of times stronger than Earth's, capable of twisting and snapping with incredible force. In some neutron stars, these magnetic fields create dazzling beams of electromagnetic radiation, pulsars, sweeping the cosmos like cosmic lighthouses. Yet, for all their violence and mystery, neutron stars are also laboratories for the laws of physics. By studying the way they spin, the signals they emit, and the gravitational waves produced when they collide, scientists can test theories of gravity, quantum mechanics, and the behavior of matter under the most extreme conditions imaginable. Each discovery brings us closer to understanding not only what lies within a neutron star, but also the fundamental building blocks of the universe itself. So what's inside a neutron star? At its surface, a crust of tightly packed atomic nuclei. Deeper within, a superfluid ocean of neutrons. And at its core, perhaps the most exotic matter in the cosmos, quarks, gluons, and particles that defy the imagination. The heart of a neutron star is a place where the known laws of physics are stretched to their breaking point, offering us a glimpse into a universe stranger and more fascinating than we ever dreamed.